Imagine trying to write, like, a switch statement for reality.
Oh, man. Good luck with that.
Right? Like, if pixel 00 is black and pixel 01 is white, print fluffy cat.
Yeah, it's completely impossible.
It really is. I mean, for decades, traditional coding just broke down entirely when it faced the sheer ambiguity of the real world.
Exactly.
You simply cannot write an explicit rule that teaches a machine that the text string fluffy cat perfectly matches some specific chaotic collection of pixels on a screen.
No, because you can't hard code every single variation of lighting or angle or, breed.
Exactly. So welcome to the deep dive. If you're a software engineer or a developer tuning in, maybe staring at a glowing IDE late at night right now.
Or just commuting.
Yeah, or commuting, and you're just looking to level up your mental models on AI architecture, well, we are speaking directly to you today.
We really are.
Our mission today is to pull apart one of the most monumental leaps in AI. Basically, how models finally learn to bridge the gap between what they read and what they actually see.
Yeah. And it is a massive paradigm shift in systems design.
Huge.
We're dissecting some really fascinating notes today from the LLM Mastery course material. Specifically, it's an excerpt from their module on transformer models and practical tricks.
Which is great stuff.
It is. And the core problem you just described, the failure of explicit, rigid programming when dealing with reality, is exactly what this material addresses.
Right.
Because for a long time, machine learning wasn't much better than those impossible switch statements. We relied on incredibly rigid classification systems.
Yeah, developers had to build pipelines to hand label, millions of images?
Millions. Just explicitly telling the model, this bucket is a cat and this bucket is a dog.
So the model just learned to sort data into these super narrow, predefined schemas.
Exactly. It's just a gigantic mapping exercise, and the human is the bottleneck there.
Right. But the course material points to a completely different approach, one that throws those rigid schemas totally out the window.
Thankfully.
Yeah. So if we aren't explicitly defining what a cat is, what's the actual mechanism for teaching a model to connect these, completely different types of data?
Well, the mechanism is called contrastive learning.
Okay.
Instead of teaching a model strict definitions, you teach it relationships. You do it through comparison.
Like this is similar to that.
Yeah. You feed the system pairs of data specifically, positive pairs and negative pairs. And the engine that actually calculates and enforces all this learning is a mathematical function called InfoNCE loss.
Okay, wait, let's drill into that for a second. Because in standard machine learning, loss is just the metric of how wrong the model's prediction is, right?
Right, yeah.
And the optimizer's whole job is to minimize that number. But how does InfoNCE actually calculate that wrongness without a predefined label?
So it does it by operating in what we call a shared embedding space.
Yeah.
Think of this as a massive multi-dimensional mathematical landscape.
Like a giant graph.
Sort of, yeah. When you take a text description, like a dog catching a frisbee, and an actual image of that event, that right there is a positive pair.
Got it.
The InfoNCE loss function mathematically measures the physical distance between those two pieces of data in that high-dimensional space.
InfoNCE, that stands for Information Noise Contrastive Estimation, right?
Got it. And what it does under the hood is calculate the cosine similarity between the vector representation of the text and the vector for the image.
So it's literally just looking at the angle between the two vectors.
Exactly.
If they point in the exact same direction, the similarity is super high.
Right. And the function's numerator wants to maximize that similarity for the positive pair. It's effectively pulling them closer together in the geometric space.
Okay, but it's contrastive, so there has to be a push too, right?
Yes. Crucially, it also has a denominator. It simultaneously compares that text against a batch of random, completely unrelated images. Those are the negative pairs.
Oh, okay.
It minimizes the similarity there, actively pushing the mismatched data apart.
So wait, this is like sorting a massive, chaotic laundry pile of socks in the dark.
Oh, I like that analogy.
Right, like you don't need to know the textbook definition of a crew sock or an ankle sock.
No.
You just know, hey, these two feel the same and belong together. That's your positive pair, and that one over there is different and belongs in another pile, your negative pair.
That's a highly accurate way to frame it for a developer, honestly. You're mapping relationships through geometric distance instead of schemas.
Right.
In that embedding space, the vector for the word dog ends up physically close to the vector for a picture of a dog. simply because the model has been rewarded for pulling matching pairs together.
And punished for keeping them apart.
Right, pulling matching ones together and pushing mismatched ones apart millions and millions of times.
So you literally just throw raw paired data at the system.
Yeah, like images and their alt text just scraped directly from the internet.
And the geometry just sorts out the underlying semantic meaning on its own.
Without a single human having to write a classification label.
Okay, the math makes total sense in theory. But practically speaking, I mean, text strings and pixel arrays are entirely different data structures.
They really are.
So how do you physically pipe a JPEG and a string of text into the exact same mathematical space in the first place? They require completely different processing logic.
This is where the actual architecture comes in. The source material highlights a really famous model called CLIP.
Right. Contrastive language image pre-training.
Exactly. To solve that exact data structure problem, CLIP uses a dual-encoder setup. It basically has two completely separate processing pipelines.
Okay.
On one side, you have a text encoder, which is just a standard transform model processing language tokens. And on the other side, you have a vision encoder.
And the notes specifically call out the use of VIT, right? Vision transformers.
Yes, they do.
Let's pause on VIT for a second, because transformers were originally built for sequential data, like sentences where one word follows another.
Right, left to right.
But images aren't sequential at all. They're 2D grids of pixels. So how does a vision transformer process a grid to make it compatible with the transformer architecture?
Well, it takes a very clever, almost brute force approach to serialization.
Really?
Yeah. A vision transformer literally chops the image up into a grid of fixed size patches, say 16 by 16 pixel squares.
Oh, wow. Okay.
It flattens those patches into linear vectors, adds positional embeddings so the model knows where each patch came from in the original grid, and then feeds them into the transformer sequence.
So it literally treats those image patches exactly the same way a text transformer treats words in a sentence.
Exactly the same way.
That is fascinating. So the text encoder breaks a sentence into word tokens, and the vision encoder breaks an image into pixel patch tokens.
You've got it.
But the notes say these two encoders process their respective inputs completely independently.
Yeah.
I mean, for a developer, this sounds like having two separate microservices running on totally different tech stacks, not sharing an API. It's somehow expected to output perfectly synchronized, directly comparable data formats.
That's a great way to look at it.
If they never actually talk during processing, how do they ever align?
Your microservices analogy is perfect here, because the vision encoder only knows about pixel patches. The text encoder only knows about language tokens.
Right.
They do not communicate while parsing the input at all. But the API contract they share, the integration test they both have to pass, is that shared embedding space created by the InfoNCE loss function.
Ah, so the training loop itself is the CI/CD pipeline enforcing the contract.
Precisely. During training, the vision microservice spits out a 512-dimensional vector for the image.
Okay.
The text microservice spits out a 512-dimensional vector for the caption. The InfoNCE loss function looks at those two vectors, calculates that cosine similarity. It basically says, hey, you two came from a matching pair of data, but your output vectors are pointing in totally different directions.
Fix it?
Yeah, update your internal weights so your outputs land closer together next time.
Wow.
So they work independently,
Yeah.
but they are relentlessly forced to project their separate understandings of the world into the exact same coordinate system.
And because CLIP successfully maps language and vision into this, universal coordinate system, it unlocks a capability that just totally upends standard ML deployment.
Oh, absolutely.
The course material calls it zero-shot classification.
Yes.
Let's contextualize why this is such a massive operational win for a second. In traditional ML, say you build an app that identifies inventory in a warehouse.
Okay.
You train it on boxes, pallets, and forklifts. But tomorrow, the company introduces a new automated robot cart.
Right, an edge case.
When your camera sees the cart, the model either crashes or it hallucinates and calls it a weird forklift.
Yeah, a really weird forklift.
And to fix it, you have to go gather thousands of images of the cart, label them by hand, retrain your entire model, run regression tests, and redeploy the whole pipeline.
It is a massive, expensive, highly brittle feedback loop. Every single new edge case requires a full system update.
But with zero-shot classification via CLIP, you bypass that entire pipeline.
Entirely.
How does the shared embedding space actually allow us to just skip retraining?
Because CLIP has already learned the fundamental relationship between human language and visual concepts.
Okay.
You don't need to show it 1,000 pictures of a new robot cart. You just provide a list of text strings representing the categories you want to look for at runtime.
Oh, wow.
You just type out a photo of a box, a photo of a pallet, and a photo of an automated robot cart.
Wait, really? This is the equivalent of writing a function that somehow perfectly handles an edge case input you never explicitly programmed it to catch just because it read your documentation?
Yes. You just pass it new documentation. You feed those text strings into CLIP's text encoder.
Okay.
It converts each phrase into a vector in the embedding space. Then, when your warehouse camera captures a new frame, the vision encoder turns that image into a single vector.
And it just compares them.
This system just measures the distance between the image vector and your various text vectors. Whichever text vector is geometrically closest, well, that's your classification.
Boom, it's a robot cart.
Boom.
I mean, from an engineering standpoint, this is mind-blowing. You are decoupling the model's architecture from the specific categories it needs to recognize.
Completely.
The output layer isn't hard-coded anymore, it's just a dynamic variable passed at runtime. You want to add 1,000 new categories to your app. Just pass an array of 1,000 new text labels.
And the geometry just handles the routing for you. It completely removes the friction from the software development lifecycle when you're building AI applications.
That's incredible.
You're no longer training a model to perform a specific task. You are querying a generalized foundational space.
Okay, so CLIP is basically an incredibly powerful search and routing engine. It takes text, converts it to coordinates, and finds the closest matching image vector.
Exactly.
But finding an existing image is fundamentally different from drawing one from scratch.
Very true.
Yet the notes claim this exact same architecture is the foundation for modern AI image generation.
It is.
I have to push back here, though. How do we leap from measuring distances between existing vectors to actually hallucinating brand new pixels out of thin air?
That is the pivotal shift from understanding to
Right.
creation, really.
Yeah.
And you're right, the CLIP alone doesn't generate images.
Right.
When you type a prompt into Midjourney or DALL-E, the actual pixel generation is handled by a diffusion model.
Okay.
But diffusion models on their own are basically blind painters.
Blind painter.
Yeah, they start with pure visual static, random Gaussian noise, and step by step, they remove that noise to reveal an image.
But if they're just removing noise, how do they know what shapes to leave behind?
That is exactly where CLIP comes in. The diffusion model needs a blueprint.
Ah.
It needs to know that the pixels it's uncovering actually align with the user's text prompt.
Yeah.
And it achieves this integration through a mechanism called cross-attention.
Cross-attention. Okay.
At every single step of the denoising process, the diffusion model looks at the text embeddings generated by CLIP.
Let's dig into the math of that cross-attention layer for a second, because looking at is a bit too, abstract for us.
Fair enough.
In a transformer, attention usually involves query, key, and value matrices. How do the diffusion model and the CLIP model map to those specific matrices?
Excellent question. So in this cross-attention setup, the queries come from the diffusion model itself specifically, the spatial features of the noisy image at that current step.
Okay.
The diffusion model is essentially asking, for this specific patch of noisy pixels, what information do I need?
And the keys and values.
The keys and the values come directly from the CLIP text embeddings of your prompt.
So the diffusion model generates a query based on the static and tests it against the keys of the text prompt.
Yes. The model computes the dot product between the spatial queries and the text keys to generate an attention map. This map tells the diffusion model exactly which words in the text prompt are most relevant to which specific pixel patches in the image at that exact moment.
That's crazy.
And then it uses the values, the actual semantic weight of those words, to update the image, physically steering the denoising process.
It's like a continuous mathematical steering mechanism. I had this analogy in my head of CLIP acting like a strict art director standing over the artist's shoulder, shouting, "Add more neon here."
Yeah, make it more cyberpunk.
Exactly. But it's actually far more integrated than that. The diffusion model is constantly calculating the mathematical relevance of every single word in the prompt against every single spatial patch on the canvas,
Thousands of times a second.
using the coordinate map that CLIP provided.
Exactly, because without CLIP's text embeddings, the diffusion model would just generate beautiful, high-resolution, completely random nonsense.
Right.
CIP is what grounds the generative process in human intent. It provides the anchor in the embedding space, and cross-attention is the tow cable pulling the noisy pixels toward that anchor.
Wow. So we've got text and images perfectly aligned. We've bypassed rigid training schemas for zero-shot classification, and we're using those same vector coordinates to steer the generation of entirely new worlds from pure static.
It's a lot.
It is. But if the math of this embedding space is this robust, I mean, if we can calculate the distance between a string of characters and an array of pixels, why limit ourselves to just those two data structures?
And that leads us to the bleeding edge of the course material, the multimodal future.
Yes.
The notes state very clearly that the contrastive learning paradigm generalizes far beyond just vision and language.
Right. The lectures specifically dive into a model called image bind. And structurally, this completely breaks open the possibilities, doesn't it?
Oh, it really does.
Image bind takes the exact dual-encoder contrastive approach of CLIP, but instead of just a text encoder and a vision encoder, it brings in separate encoders for audio, depth maps, thermal data, and even inertial motion data.
Yeah, and if we look at the system architecture, it proves that the InfoNCE loss function isn't just a clever trick for photos and captions.
It is a foundational blueprint for sensory alignment. What ImageBind does is take that central shared embedding space and use images as the core anchor to bind everything else together.
Okay, walk me through that. How does an image act as an anchor for audio or thermal data?
Well, think about how data naturally co-occurs in the real world.
Okay.
A video clip of a train pulling into a station has a visual component, sure, but it also has an audio track of screeching brakes.
Right.
A video of a campfire pairs naturally with a thermal heat map showing high temperatures.
Oh, I see.
ImageBind takes those naturally occurring pairs and applies the exact same contrastive learning logic. It pulls the vector for the screeching audio and the vector for the train image closer together.
And pushes the unrelated ones apart.
Right. It pulls the thermal data and the fire image closer together. Because everything's being pulled toward the visual anchor, all 6 modalities end up projected into the exact same vector space. So the system learns that the audio file of a dog barking, the text string a dog barking, the visual pixel array of a dog, and the thermal signature of an animal all belong in the exact same mathematical neighborhood.
Yes. They become mathematically interchangeable.
I am geeking out over the architectural possibilities here. I mean, imagine building a totally new kind of search engine or data retrieval system.
Oh, the applications are endless.
Because right now, data is incredibly siloed, right? Text searches text, reverse image searches images. But with a unified space like ImageBind, a user could literally input a thermal heat map file as their search query, and the system could natively return an audio clip of what that heat signature likely sounds like.
Or generate a text description of the event.
Yes, you wouldn't have to write complex, brittle translation layers between an audio processing pipeline and a text pipeline. They all just speak the same vector language natively.
It raises a really profound point about where AI architecture is heading. We are moving away from isolated, narrow processing models toward a synthesized, multisensory understanding of the world.
It's completely breaking down the silos.
It is. And if you think about it, this is much closer to how human perception actually works.
How so?
Well, when you experience a thunderstorm, you don't process the visual lightning, the audio thunder, and the text concept of a storm in completely separate, isolated databases in your brain.
Right, they're not microservices up there.
No, there are deeply interconnected facets of the same core concept.
They all share the same neural space.
Exactly. And by expanding contrastive learning to include audio, depth, and thermal data, we are giving these computational models a much more holistic, human-like architecture for perceiving reality. We're teaching them to understand concepts, not just parse data types.
That is incredible. Let's zoom out and recap this journey because we've covered some serious architectural ground from the LLM mastery lectures today.
We really have.
We started with the sheer impossibility of writing explicit rules to connect text and images, and saw how contrastive learning and the InfoNCE loss function solve that by mapping relationships through geometric vector distance.
And then we broke down how CLIP utilizes a dual-encoder architecture, right? Taking sequence-based transformers for text and patch-based vision transformers for images, and basically forcing them to align in a shared mathematical API through CI/CD-style training loops.
Which gives developers the absolute superpower of zero-shot classification, letting us dynamically route and categorize new inputs on the fly just by passing natural language arrays.
Completely bypassing the operational nightmare of retraining.
Exactly. We then explored the generative side, detailing how diffusion models use query, key, and value cross-attention matrices to continuously test noisy pixels against CLIP's text embeddings.
Steering the generation of brand new images.
And finally, we looked at how models like ImageBind are expanding this exact same geometric mapping to include audio, thermal, and depth data, creating a unified sensory engine that treats all data types as mathematically interchangeable.
It's a fundamental shift in systems design.
So to the software engineers and developers tuning in underneath all the hype, the buzzwords and the magical seeming outputs of modern AI, there are these incredibly elegant, concrete architectural patterns.
It's not magic.
It's not. It is geometry. It's multidimensional vector space. It's clever loss functions, forcing independent microservices to agree on a shared reality.
We are moving from explicitly programming rigid rules to designing mathematical spaces where concepts organically organize themselves based on relationships.
So as you head back to your code or finish up your commute, I want to leave you with one final thought to mull over.
Okay.
We've talked about mapping text, images, thermal data, audio, and motion all into the exact same shared mathematical space. The geometry perfectly aligns these totally different forms of data into a unified map.
Right.
But at what point does that space stop being just a clever data structure we engineered for retrieval and start becoming a universal underlying language of reality? Like a fundamental map of physics and concepts that the AI now understands even better than we do.
That is a wild thought to leave on.
Thanks for joining us on the Deep Dive. Keep building, keep questioning, and we'll catch you next time.